Hello everybody and welcome to our webinar. My name is Vladimir and together with my colleague Alex, we will discuss calculation of the impedances for printed circuit board traces with QuickField. But before we start speaking about this, let me briefly outline capabilities of QuickField software for those who never heard of it. QuickField is a finite element analysis system for simulating over a variety of problems in electrical engineering, aerospace design, thermal engineering, biology, medicine, and other fields of science and technology. Set of analysis models include three suites: magnetic, electric, and thermostructural, which may be further split into DC magnetics, AC magnetics, transient magnetics, electrostatics, DC, AC, and transient conduction, static and transient heat transfer, and stress analysis models. These types of analysis may be performed individually or in combination, which make QuickField a powerful tool for complicated multi-physics analysis. This slide shows types of field coupling directly supported by QuickField. Directly means that there are more sophisticated ways to perform complicated studies. Their core QuickField functions are not enough. QuickField features open object interface, which we call ActiveField. And this is a technology for combining QuickField with other software applications, including Microsoft Office components, MATLAB, or other custom programs written on many current development platforms: C++, Python, Java, etc., etc., etc. And most important, this variety of features is extremely user-friendly and implemented such a way that basic operations with QuickField may be performed without any dedicated training. This means that QuickField customers range from high school students who need simple field mapper for school project to most advanced projects run by national laboratories, NASA, leading technological corporations like Siemens or Sony, top scientists and engineers around the world. What is particular application where QuickField is most efficient is very hard to say. There are so many fields where QuickField is proven effective. Today we will show you how to use QuickField for designing the printed circuit boards. Specifically, how to calculate the microstrip impedance, differential impedance, capacitance, and inductance matrices for particular trace design. Together with losses calculation, which also may be estimated with QuickField, this gives the printed circuit board designer all information he needs for calculating of the board or transmission lines parameters. My colleague Alex will use this application to demonstrate using of QuickField both via its user interface and through its programming interface ActiveField. Now let's see and listen to Alex's live presentation. Thank you.
On this webinar we will review 6 examples. The first example is the microstrip line, and we will calculate the impedance of this microstrip line. In the second example, we will calculate the differential impedance of the line that consists of the pair of conductors. Then we will calculate the parameters of the equivalent circuit to simulate transient pulse propagation. And we will run the transient simulation and take a look how the pulse propagates through the transmission line. These are 3 basic examples, and there are 3 advanced examples. We will calculate the losses in traces and in dielectric. Then, in the next example, we will calculate the 3-dimensional problem. Some configuration requires 3-dimensional analysis, so we included the 3-dimensional example here. And the last case, we will calculate the capacitance and inductance matrix in case of multi-trace line. Now here is the first example. This is the microstrip line. It consists of a copper trace laid on the dielectric layer, and there is the grounded reference plate on the other side of the dielectric. The dimensions in micrometers are listed here in the table, and for your convenience there is the American dimensions, which are the thousandths of an inch. The line carries the signal at frequency of 100 MHz, and our task is to calculate the impedance of the line. The impedance of the line can be calculated as a square root of self-inductance to self-capacitance ratio. So our task is to calculate the self-capacitance and the self-inductance. The geometry model is very simple, so I will create the problem from the very beginning. First I will calculate the capacitance. So to calculate the capacitance I need the electrostatic problem. I specify the problem name. The problem type is electrostatics. Now here is the geometry model editor. I will switch to the microns. Now I will draw the geometry model. First I will draw the trace. The trace has the height of 35 micrometers. And the trace has the width of 200 micrometers. That is the trace. The dielectric board has the thickness of 420 micrometers. So this would be the board. And below the board, on the other side from the trace, there is the reference plate, the grounded plate. The plate thickness is 35 micrometers. This is the reference plate. Now, of course, the board is much wider than the trace, so I will move these boundaries, say for 100 micrometers, 1000. Now that's the geometry model. This would be the trace, this is the dielectric, and this is the reference plate. To calculate the capacitance, I will assign some electric potential on the trace and will calculate the electric field distribution. In fact, the field is not only placed inside the dielectric, but also the field propagates in the air, so I should add the air block. This would be the air block surrounding my Microstrip line. Now let's assign the labels to each object. As I said, this is the air. This is the dielectric. There is no electric field inside the conductors. The electric charge is distributed along the surface of the conductor, so there is no need to label the inside of the conductor. Instead, I should give the label to the conductor surface. So this is the trace surface. And the same is true for the reference plate. This is the ground surface. And far away from my transmission line, the field fades to 0, so on the external boundary I will specify 0 electric potential. This is the external boundary. Now I have the geometry objects labeled, and next I should specify physical properties for each object. For air in electric problem, I specify the electric permittivity. This is the relative value. For the dielectric, I specify the electric permittivity of the dielectric, 4.3. On the external boundary, I specify 0 electric potential. Ground surface, the reference plate has 0 electric potential too. And the trace has the potential of 1 volt. I finished with the specifying the material properties. Now I can run the simulation. But before I run the simulation, I will build the finite element mesh. Just paste this button. Save all problem files, and now run the simulation. Here you can see the electric field distribution in the transmission line. And my task is to calculate the capacitance. The capacitance can be calculated as the ratio of the charge to the potential difference. So I need to calculate the charge on the trace. To calculate the charge, I will build the integration contour and surround the trace, then follow to integral calculator, and this is the charge. If I divide the charge by the potential difference, and I remember that the electric potential of the trace is 1 volt, and the electric potential of the ground is 0. So if I divide this charge by the potential difference, I will get the capacitance. And this is the capacitance per meter of length. If you open the problem properties, you can see that the problem length is 1 meter. You can adjust the length of the problem. For example, if I would like to calculate the capacitance per 1 inch, here it is, the capacitance per 1 inch of the length. And in most suitable form, it's 1.57 picofarads per inch. Now this is the self-capacitance of the transmission line. Next, I should calculate the inductance of the transmission line. To calculate the inductance, I will run the AC magnetic problem. So I create the new problem. The problem type is AC magnetics and the frequency is 100 megahertz. In fact, the geometry model is the same, so I simply will copy the geometry model from the electric to magnetic problem. Here it is. You may note that not only the geometry model was copied, but also the labels was copied too. In fact, the current flows inside the conductor, so I have to label the body, not the surface as it was in electrostatic problem, but the body of the trace. And the body of the ground plate. Now that's all, and again I should assign the physical properties for each object. In magnetic problem I specify the magnetic properties. For the air I specify the magnetic permeability of 1. For the dielectric I specify the magnetic permeability of 1. For the trace I specify the magnetic permeability of copper, the electrical conductivity of copper, and the total current of 1 microampere. This is the direct current, and the back current eventually will flow in the ground plate. So for the ground plate I will specify the permeability and conductivity of copper and the back current minus 1 microampere. Now these labels were used in electrostatic problem. I do not need these labels in magnetic problem, so I leave these controls unchecked. And you see the label has the 0 sign. That means that this label has no meaning in this problem. And far away from my transmission line, the magnetic field fades to 0. So on the external boundary I specify 0 magnetic potential. Now again build the finite element mesh, save the files and run the simulation. And here you can see the magnetic field distribution. And the color map indicates the current density distribution in the conductor. We might need to refine the mesh. QuickField initially builds the mesh with respect to geometrical form of the object. The larger the object, the larger the mesh element size. The eddy current are distributed in thin layer at the conductor surface, and we need extremely fine mesh here to accurately calculate the current distribution. So once the problem is solved, you may apply the automatic mesh refinement. To do so, simply press Solve and Refine button. You may see how the mesh was refined at the edge, and here is the result. Now let's calculate the inductance. There are two ways that you can calculate the inductance. The inductance is equal to the ratio of the magnetic flux to the current. And the second option is the inductance is the double magnetic field energy divided by the current square. It is more suitable to use this option with QuickField. So I will open the integral calculator and start the inductance wizard. Here I will switch to the stored energy calculation approach. I will calculate the energy, and here is the current that flows in the trace. And this is the inductance. Again, this is the inductance calculated per 1 meter of length. You can change the problem properties. And recalculate the inductance. Now here is the inductance per 1 inch of length. And in more suitable form, it is 13.8 nanohenry per inch. Now I know the self-capacitance and the self-inductance, and I can calculate the impedance of the line. I should divide the inductance, the self-inductance, by the self-capacitance, which is 1.57 times 10 to the power of minus 12. And I should calculate the square root of this value. Now the impedance of my transmission line 39.75 ohms. So that's it. Let's now move to the next example. And this is the case of the transmission line that consists of the pair of conductors laid on the dielectric board, and on the other side of the board there is the reference plate. Dimensions of the board and of the conductors are the same as in the previous example. The distance between traces is 130 micrometers. And our task is to calculate the differential impedance of this transmission line. To calculate the differential impedance, we need to know the differential inductance and differential capacitance. So again, I will start QuickField and create new electrostatic problem. The geometry model is very simple. You can draw the model or you can import it from the AutoCAD. I already have the geometry model drawn in the AutoCAD, so I simply will import it. Now this is the geometry model. Now I should assign labels to each geometric object. This is the air. This is the external boundary. I hold the Ctrl key pressed to select multiple objects. This is the dielectric board. Again, there is no electric field inside the conductor, so I give the labels to the conductor surface only. This is the trace 1. This is the trace 2nd. And this is the ground plate. Next, I should assign the physical properties for each label. For the air, I specify the electric permittivity of air, which is 1. For the dielectric, I specify the electric permittivity of the dielectric, which is 4.3. For the trace 1, I specify the electric potential. It would be minus 0.5 volts. And for the second trace, I specify the same electric potential with a different sign, which is plus 0.5 volts. The ground plate has 0 electric potential. And far away from my transmission line, the electric field fades to 0. So at the external boundary I specify 0 electric potential. Now let's build the finite element mesh, save all the files and run the simulation. Here you can see the electric field distribution in the transmission line. And again my task is to calculate the capacitance. And the capacitance can be calculated as the ratio of the charge to the potential difference. And to calculate the charge, I will build the integrational contour around the trace. And here is the charge. The potential difference is 1 volt. I have plus half of the plus 0.5 volt on the second trace and minus 0.5 volts, so the potential difference is 1 volt. So the capacitance is this value farads per meter. I have the model depth of meter. I will correct this, and here is the value. This is the capacitance per inch of the length. Farads per inch. And in more suitable form, this is 1.23 picofarads per inch. This is the differential capacitance. Now let's calculate the differential inductance. Again, I will create a new problem, which would be AC magnetic problem. So I change the problem type to AC magnetics, and the frequency is 100 Hertz. 100 megahertz. I will switch to inch right away. Now, as the geometry model is the same, I will simply copy this geometry model here. Now let's check the labels, air, dielectric, and also I have the labels for the traces. The labels used in electrostatic problem is not suitable for the magnetic problem. So I give the label to the conductors. Trace 1. This is the conductor label, this is the surface label. Trace 2. And the ground plate. In magnetic problem, I should specify the magnetic properties of the materials. So for the air, I specify the magnetic permeability, which is 1. The magnetic permeability of the dielectric is 1. The ground plate is made of copper and it features the magnetic permeability of 1. and the electrical conductivity of 1. And the total current in a reference plate is 0 because I have the direct current here and back current here in the second trace. So there is nothing for the ground plate. Trace 1 is made of copper, and I specify the electrical conductivity and the permeability of copper here. And as I assign some electric current, which is 1 microampere. For the second trace, which is made of copper, I specify the physical properties of copper, and I assign the back current, which is -1 microampere. Now these labels were used in electrostatic problem. I do not need them in magnetic problems, so I leave all the controls unchecked. You may note again the 0 sign on the label, which means that this label is not used in the analysis. And for the external boundary, the fields fades to 0 when far away from the transmission line. So for the external boundary, I specify 0 magnetic potential. Now again, let's build the mesh and run the simulation. Again, remember that QuickField uses large element size for the large object and small element size for the small object, but it doesn't take into account the physics, the results. To take into account the physics, you should refine the mesh Now you can see that there is the much denser mesh on the surface where the eddy current flows. Now let's calculate the inductance. Again, I will use the energy approach, and the inductance is the double energy divided by the total current square. So I run the integral calculator, start the inductance wizard, switch to the stored energy approach, and here is the inductance. As I already switched to the inch, this is the inductance per inch of length. And in most suitable form, this is 15.99 nanohenry per inch. This is the differential inductance. Now let's calculate the impedance, the differential impedance. I need to calculate the differential inductance by the differential capacitance and then find the square root. 111. So the differential impedance is 111 ohms. The next case is the simulation of the pulse propagation through a transmission line. It is the same transmission line that was in our first example. The line length is 5 inches and the self-inductance and the self-capacitance of the line are calculated using our first example. These are values per the full length of the line, which is 5 inches. To simulate the pulse propagation, we construct the electric circuit that contains a number of LC chains connected in series. The number of chains depends on the pulse time parameters and the time delay of the transmission line itself. For this specific transmission line, it is required to have at least 30 chains. Now let's first simulate the case when the load impedance matches the line impedance and the source impedance match the line impedance. I will start QuickField and open the simulation file. Here you can see this is the transient magnetic problem. Well, each QuickField problem should have the geometry model. In fact, there is no geometry model in this case, but I have to draw some model. So this is some geometry model which consists of the single triangle. But the part we are interested in is the electric circuit. So this is the electric circuit. There are 30 chains in the electric circuit. There is the voltage source, which provides the pulse of 2 volts, and the duration of the pulse is 5 nanoseconds. This is the impedance of the source, and the line is connected to the load, and the load has the matching impedance of 25.5 ohms. Now let's run the simulation. I will adjust the screen and switch off this table. Now, when the driver launches a signal onto the transmission line, the magnitude of the signal depends on the voltage and the source resistance and the impedance of the transmission line. The initial voltage seen at the driver will be governed by the voltage divider of the source resistance and the line impedance. In the end of the transmission line, here, if the end of the transmission line is terminated with the impedance that exactly matches the characteristic impedance of the line, the signal will be terminated to the ground and the voltage will remain on the line until the signal source switches again. Now let's check it. With the green line you can see the voltage of the driver. With the red line you can see the voltage as it's seen on the transmission line. You see there is no ripple, no back wave, because the impedance of the transmission line is matched with the load impedance. Now let's take a look at the voltage at the load. You can see it's the same 1 volt, but there is the time delay between the moment when the voltage pulse started at the beginning of the line and the moment when the voltage pulse arrived at the load. And this delay is the time delay of the transmission line. If the end of the transmission line exhibits some impedance other than the characteristic impedance of the line, a portion of the signal will be terminated to ground and the remainder of the signal will be reflected back down to the transmission line toward the source. And the amount of the signal reflected back is determined by the reflection coefficient. With open load, the reflection is 100%. So this large resistance will simulate the open load condition. And in this case, on the source, here we will have the double value of the signal. Now let's run the simulation and take a look at the result. Here I will measure the voltage on the line. You can see initially the 1 volt was induced on the line, and then the reflection came and the voltage doubles to the value of 2 volts. If we have the shorted load, the reflection again is 100%, but it has the negative value. Let's again measure. You see again, it was initially, the voltage was initially shoot at 1 volt, but then the reflection came and the voltage dropped to 0. You can also study other cases of the impedance mismatch. For example, if I set the load to be 50 ohms instead of 95.5, which is the characteristic impedance of the line, there will be a reflection wave, and here you will see it. So again, initially the voltage shoots to 1 volt and then the reflection came. You can also study other cases of the impedance mismatch. If the source impedance is larger than the line impedance, it is referred as the underdriven transmission line. And if the source impedance is smaller than the line impedance, it is known as the overdriven transmission line. And we move to the next example. In this example, we will need to simulate non-ideal transmission line and calculate trace resistance and the shunt resistance to be included in the line equivalent circuit. The resistive losses occurs in the trace, both in the trace and in the reference plate. And the resistance value is not constant. It depends on frequency. At high frequency, the skin effect, which is shown in red, manifests itself. At low frequency, the resistance and inductance assume DC values, but as frequency increases, the cross-sectional current distribution in the transmission line becomes non-uniform and moves to the exterior of the conductor. The changing current distribution causes the resistance to increase with the square root of frequency. Now let's run the simulation and compare the resistance value at different frequencies. Here I start QuickField. And this is the problem. This is the same geometry model of the Microstrip transmission line, which consists of the single trace laid on the dielectric board, and there is the ground plate on the other side. The problem type is AC magnetics. Again, I will change the length units to inches. Now let's run the first case. The frequency was of 100th of the hertz. So it will be DC case. Now here you can see the magnetic field distribution and the electric current density distribution. Now let's calculate the resistance and the inductance of the line. Now here is the resistance. And the inductance is this value. These are inductance per inch of length and the resistance per inch of length. And this is the case of frequency. This is DC case. Now let's change the frequency. For example, 1 kilohertz. And run the simulation again. Again, I will use the impedance wizard to calculate the resistance. You see no change. And the inductance. Again, no change. So 1 kilohertz is equal to the DC mode. Now again, let's change the frequency. It would be 100 kilohertz. Here is the simulation result. Again, I run the impedance wizard. And now there is slight change in the inductance, in the resistance. And some change in the inductance. Now let's again change the frequency to the 1 megahertz. Now this is the resistance. And this is the inductance. And the last, let's run the last simulation. 100 megahertz. Again, I will calculate the impedance of the trace. Now you can see how the resistance and how the inductance of the transmission line change with the frequency. So we know the R and L parameters here. In most designs, the dielectric losses are ignored because the conductor losses are dominant. But as frequency increase, the dielectric losses increases too. The typical method of dielectric loss characterization is by the loss tangent. QuickField solves the Maxwell equation, and we may include the dielectric losses in Maxwell equation if we invent the imaginary part of the dielectric permittivity. And this imaginary portion represents the losses, and the real portion represents the typical value of the dielectric constant. And since the imaginary portion represents the losses, it is convenient to think of it as the effective conductivity. Again, I will start QuickField. And open the simulation case. The problem type is AC conduction, and I specify the real frequency at which the circuit board operates. It's 100 MHz. I will switch the length units to the inches. Now let's take a look at the geometry model. It's the same geometry model. Here again I have the air, I have the dielectric board, I have the trace, and I have the ground. At the trace surface I specify the electric potential of 2 volts, and the ground plate has the electric potential of 0 volts. And for dielectric I specify the electric permittivity and the effective electrical conductivity, which is 430 microsiemens per meter. Now let's run the simulation and take a look at the results. Here is the electric field distribution. I will adjust the picture so we will see the color map of the current density and the vector plot of the current density. This is how the current flows in the lossy dielectric. And this current represents the way to calculate the shunt resistance of the dielectric. To calculate the resistance, I should divide the potential difference by the current. Now the potential difference is 2 volts. My trace has the potential of 2 volts and the ground plate has the potential of 0 volts. And to calculate the current, I will use the contour tool. I will build the integrational contour and calculate all the current passing through my contour. here is the current. Now if I divide the potential difference by the current, I will get the resistance, which is 68 kilo ohms. No, it's as you see, indeed, the shunt resistance is much larger than the conductive resistance. Here is the case that requires the three-dimensional analysis. There are two traces crossing, and our task is to calculate the crosstalk. To calculate the crosstalk, we need to know the differential capacitance and the differential inductance. The dielectric board is multi-layered. There are two layers. The first layer has the dielectric permittivity of 4.3 and the second layer has the dielectric permittivity of 4.6. Now this case could be simulated with QuickField. Now let's first take a look at the geometry model. Initially, the geometry model was constructed as two-dimensional, and then we will use the extrusion option to build the three-dimensional model from this two-dimensional sketch. Now this is the three-dimensional model, and in this model we have the air block, we have the dielectric layer 1 and the dielectric layer 2, so there are two dielectric layers. And there are two traces. This is the trace 1 and this is the trace 2. And there is the ground reference plate at the other side, at the bottom of the dielectric board. To calculate the differential capacitance, again I assign positive voltage to one trace and the same but negative voltage to the other trace. The ground plate has the 0 voltage. And if I run the simulations, here are the simulation results. This is the voltage distribution. Here I can adjust the field picture. This is the equipotential surfaces. But my task is to calculate the capacitance. To calculate the capacitance, I will use the following equation. The capacitance is the double energy divided by the voltage square. So this is the energy stored in the entire system. To calculate the energy, I will switch to the integration mode and select entire model. And this is the energy. Now the capacitance is double value of this energy divided by the potential difference square. Now it's more convenient to write it in this form. 0.16 pF. This is the differential capacitance. Now you know there is the similarity between the electric and magnetic field, as it is explained in this publication. The inductance could be recalculated from the capacitance if we calculate the capacitance and specify unity dielectric permittivity for the materials. All you have to do is to specify 1 for electric permittivity of dielectric. Run the simulation. This is the three-dimensional analysis. Again, calculate the capacitance. And the capacitance is and from this value, using this equation, you can calculate the inductance and find the impedance. We are short of time now, so I leave the calculations up to you, and we will move to the next example. Now, the last example for today is the capacitance and the inductance matrix calculation in case of multi-trace transmission line. To calculate self-capacitance, you should assign some voltage to the conductor, disconnect all other conductors, and assign zero potential to other conductors, and then you can calculate the charge stored on this conductor and divide the charge by the potential of the conductor. Then you should repeat the same procedure to each conductor, and this would be the self-capacitance. To calculate the mutual capacitance, the differential capacitance between, say, the first and the third conductor, you should assign some positive voltage here And the same but negative voltage here. Again, these conductors are connected to zero, to the grounded plate. Again, run the simulation and calculate the charge and divide the charge by the potential difference. And this you should repeat for each pair of conductors. All in all, you should run 6 simulations to calculate differential capacitance. QuickField allows to automate this task. Here you can see the geometry model. Again, we have the air, we have the dielectric board, and there are 4 traces. And there is the grounded reference plates on the top and on the bottom of the board. QuickField features the capacitance calculator that allows you to calculate the capacitance matrix automatically. All you have to do is specify which conductors should be included in the calculation and then press the calculate button. Now let's run the simulation. QuickField generates the set of problems, assigns specific laws for each pair of conductors, measure the electric energy and calculate the capacitance based on this electric energy. And as a result, you have the mutual partial capacitance matrix.